I welcome you all. One second, Pratik, have you started the live stream? Pratik?
Yes, yes, go ahead.
Okay. So last series, uh, begin. We want to thank other people and this note for action of So we with that mic to Shreya. Thank you. Okay, we will be needing 5 more minutes. There is a network error at the site of Shreya. So just pardon us and give 5 more.
Yeah, sure.
Yeah, so just give us 5 minutes. Thank you.
এই হ্যাং করে যাচ্ছে কম্পিউটারটা, ওই ইউটিউবে স্মুথ স্ট্রিমিং হচ্ছে না বলছে। মানে আমি তো করে রেখেছি, আমার কম্পিউটারটা এবার আরম্ভ করেছে, একটু রেখে দিয়েছি, এখন দেখা যাক আসছে কিনা। বুঝতে পারছি না আমি ঠিক, দাঁড়াও। এখন তো চলছে চলছে মোজিলা অফ করে দিলে তো ইয়ে হয়ে যাবে তো। হ্যাঁ,
হ্যালো।
হাই শ্রেয়া চলে এসছে।
So, hi, we have Shreya with us. So, I think Shreya, you should go ahead and start the formal introduction part.
Yes, sorry for the delay. I was having some network issue. I'm extremely sorry about it. Okay, so good evening, everyone. Let me welcome you all to the 10th lecture of the Nature as we Unfolded seminar series of CAPSS. I'm glad to introduce our today's speaker, Dr. P.N. Maya. Dr. Maya did her master's from Cochin University and moved to Institute for Plasma Research at Gandhinagar for her PhD. She received the prestigious Booty Young Scientist Award and DADD Fellowship during her PhD. At postdoc, she was awarded Max Planck Fellowship and joined Max Planck Institute for Plasma Physics and subsequently joined Max Planck Institute for Astrophysics, both in Garching at Germany. She then moved to ITER India as a visiting scientist. In 2017, she was awarded prestigious Horizon 2020 Fellowship by European Union and joined University of Greifswald near Berlin. Her research interests are energy from nuclear fusion, plasma research, plasma material interactions, charged particle, and neutron interactions with matter. Other than research, she has keen interest in socio-political issues as well. She is an avid movie buff in addition to being a cycling and running enthusiast. So, now let us welcome our speaker, and I would request Dr. Maya to start with her presentation.
Thank you, Shreya. Thank you very much.
Thank you.
I would like to thank the CAPSS seminar team for inviting me this fantastic opportunity. I have been following your lectures while in YouTube, and I'm very much honored to be part of the series. I have been listening to the great lectures by various eminent physicists and scientists. So, having that, today I would like to. Can you see my screen or?
No, not yet.
Share it? No. Okay.
Yes, you can see it. Yes.
Yeah, okay. So thank you once again for this wonderful opportunity. And today I will be speaking about the magnetic trapping of charged particles, that is, the charged particle trapping due to magnetic field, and how that lead to the pursuit of fusion energy on Earth. So currently I work in Institute for Plasma Research, Gandhinagar, and here the institute is primarily focused on fusion research and various other applications of plasma. So why do we study about fusion, or why are we even interested in fusion? Because we know that India is roughly 1/3 of the world average in the per capita energy consumption. And the per capita energy consumption, that is how much energy one consumes per person, is related to the quality of life. So in order to improve the quality of life, we need to have higher energy consumption. They are kind of intimately linked to each other. And we are primarily resorting to the conventional fuels like fossil energy, which is going to be endangered soon, and we need to have a long-term energy security. So we have to explore all sources of energy, which includes renewables, non-renewables, and all other forms of energy. And fusion is an abundant source of energy, which we know from our universe. All the energy that stars create is primarily from fusion. Besides, it is one of the cleanest sources of energy. That means there is very little environmental pollution as well as nuclear exhaust. So it is indeed worthwhile to pursue fusion. And in this talk, we shall explore some of the possibilities of fusion energy and how the fusion energy is being, let's say, pursued, and what was the efforts in pursuing that process, and what is the little bit of the basics behind it. So that's what we are going to address in this talk. We know that, as I said, stars are the factories of fusion because all the stars produce energy primarily from fusion reaction. So, if we consider our nearest star, Sun, it's producing fusion, it's doing the fusion of protons. So, we have the fundamental 4 protons combined together to form a helium nuclei, along with 2 positrons, neutrinos, and gamma rays. So, the fusion energy is produced primarily by the mass difference between the reactants, that is the 4 protons, which has a mass of 4.032 mu, and the product nucleic helium has slightly lower mass. And this difference in mass is converted to energy with the famous relation we know, E equal to delta m c square. And this particular process in Sun produces 26.22 MeV energy. Now, how Sun is achieving this fusion, or how Sun is capable of achieving this fusion reaction and producing energy, that is the fundamental thing that we are going to look at. So, in the case of Sun or any stars, which is basically when the star formation takes place, there is huge gas cloud in the space which is being compressed by gravity. Because of the gravitational compression, the gas cloud gets heated up and it starts to ionize to form something what you call plasma, which is basically a collection of electrons and ions, and of course there is some nuclear gas also. As the compression takes place, the temperature increases and the gas gets more and more converted to plasma, and eventually one reaches a state where there is sufficient internal pressure in the gas cloud or the star which balances the compression of the hydrostat, the gravitational compression. So, the star reaches a state where there is an equilibrium between the gravitational compression and the internal pressure. This particular state is what we call the hydrostatic equilibrium. This is very interesting because this is what keeps the stars intact. And we will see in the later slides how we don't have the benefit of the gravitational compression on Earth, but how we achieve that through the magnetic field. That's what we are going to see in the coming slides. So if you look at the internal pressure of the star, this is contributing from two constituents. One is the gas pressure and other is the radiation pressure. So if you take a star like Sun, then the gas pressure is, one can write it as an ideal gas, so it's proportional to the temperature of the gas, it's proportional to the density of the gas inside. And the radiation pressure, one can imagine this is a black body, so the radiation pressure is proportional to the temperature T to the power 4, which is balanced by the gravitational force. Now, in the case of Sun or any low mass stars, it's primarily the gas pressure, the plasma pressure, which is the dominant term. But if you have a star which is having higher mass, then the radiation pressure takes over. So this particular equilibrium of the radiation pressure or the internal pressure from the radiation and the gas and the gravity keeps the hydrostatic equilibrium of a star. Now, when you have a hydrostatic equilibrium, you also need to have a thermal equilibrium to be thermodynamic equilibrium. So the thermal equilibrium of the star comes from, it essentially means all the energy that is created in the core is dissipated. So there is a source of energy, which is the fusion reaction, is balanced by the sink, which is by various conduction, convection and radiation. So the core in the center of the Sun, due to the very high temperature and density, fusion reaction takes place, which creates an enormous amount of energy, and this energy is being radiated and convectively transported to the outer surface of the Sun. So that's how the thermal equilibrium of the stars will work. Now, if you look at the density and temperature in the Sun, what we see here, this is a graph which reads in German, but actually it's basically temperature, drop means pressure, dicta is density and temperature. And in the x-axis what you see is the distance, normalized distance from the core of the Sun, which is at 0, and at the edge, which is 1, the end of the solar atmosphere. In the x-axis, in the y-axis you see there is a density in kilogram per meter cube, and the temperature in the core of the Sun, which are in the Sun are of the order of 10 to the power 6 Kelvin, so the millions of Kelvin, and the pressure is in bar or atmosphere. The temperature in the Sun core is roughly of the order of 10 to the power 7, 14 10 to the power 6, that's 14, 15 10 to the power 6, so that's like 10 to the power 7 Kelvin. And it falls from there to roughly 4000 Kelvin towards the edge of the Sun. Similarly, density is also very high in the core. The number density would account to roughly 10 to the power 32 per meter cube kind of density, 32, 33. And the pressure is also very high. So, it's like 10 to the power 10, 11 atmosphere in the core. As one moves away from the core towards the outer atmosphere of the Sun, solar interior to the atmosphere, the temperature, pressure, density, everything falls down. So, in the core, the material is in the plasma state, that is, the gas is ionized to a very high temperature, and at this temperature, the material is in the plasma state and the fusion reaction takes place. Now, in order to have the fusion reaction, we know that two charged particles to come together, two like charged particles to come together, one needs to overcome the electrostatic repulsion. So if unless one goes to very high temperature, very high kinetic energy, temperature is nothing but kinetic energy, you can't overcome you can't surmount the potential barrier and have fusion reaction. So here the vertical line indicates the electrostatic potential barrier, which is at Rm. Incidentally, most of the fusion reaction happens not by surmounting the barrier but by quantum tunneling. And to achieve this particular, and the quantum tunneling probability increases with increase in the temperature. So in order to achieve fusion, one needs to have very high kinetic energy or very high temperature in the plasma. This is same whether it is in the sun or on Earth. Now on the right hand side, what you see is the binding energy per nucleon. It's an interesting quantity. What it does is that how strong an atom is bound, the nucleons in the core of an atom is bound together. So higher the binding energy per nucleon means higher the stability of the atom. It is difficult to convert that atom into something else. Whereas if you have low binding energy per nucleon means these atoms are easy to combine, these nuclei are easy to combine to higher and higher state. So if you look in the x-axis shows the atomic number of nucleons in the atom. So what one sees that in the low number of nucleon or in the low mass number atoms, it's easy to do the fusion till you reach iron. But as you climb up higher and higher, the stability of the atom increases, means you need to invest more energy to combine them. Therefore, it is easy to imagine that one could use hydrogen or hydrogen isotopes for that matter to combine to form helium is the simplest or the easiest reaction. Similarly, if you go to very high nuclear masses, it is easy to have the fission reaction, that is to split the nuclei into several constituent fragments and release a lot of energy. And this is what happened in the fission reactors or fission energy. The stars primarily do the fission reaction. And the energy gained in the fission reaction is much larger than that in the fission. Therefore, it's worth pursuing fusion. However, if one wants to bring the reactions from the sun to earth, it's not an easy job. There are several challenges ahead of us. And the first and foremost thing is how to create a fusion relevant plasma in a lab. So what you see here on the left hand side is a plot of the reaction cross section, which is basically how many reactions per unit volume per second. So higher the number of reactions per unit volume per second, higher the energy gain of that process. And in the x-axis you have the temperature. So there are three curves. The uppermost one is deuterium-tritium fusion. Deuterium is an isotope of hydrogen with one proton and one neutron. Tritium is another isotope with two neutrons and one protons. If you combine them, what you see that for a given temperature, let's say 10 keV, let's take the value of 10 keV, the DT reaction has an absolutely large compared to the gyro period or gyro radius. Let's say the circumference of that. So you can define the magnetic moment as a ratio of the magnetic half V square, which is the kinetic energy of the field, and P stands for, so we can define, the moment you have a magnetic field, you can define the velocity of a particle either parallel to the field, which is unaltered, or perpendicular to the field. So VP stands for perpendicular and V parallel stands for the parallel field. So one can define the magnetic moment as a ratio of the perpendicular kinetic energy upon the magnetic field. And this is a conserved quantity which does not change while the particle travels along the magnetic field line. So the trapping of a charged particle in a magnetic field is essentially the story of the magnetic moment conservation. In any complicated arbitrary geometry, provided the field variation is not very strong, then one can always utilize this property to understand the magnetic trapping. Now, let's say that we have a stationary magnetic field. There is no change there is no time dependence. The of the system is also conserved because the net work done by the magnetic forces is zero. So whatever energy the particle has before entering the field would be the energy in the field also. All it does is it does gyrate the particle in a helical orbit. So the parallel and perpendicular velocities parallel to the magnetic field and perpendicular to the magnetic field would change. So what happens is that if you have, now let us say that we have a magnetic field. A charged particle is gyrating around the field line, and with some parallel velocity it would exit the field. So we can't really confine a charged particle with a straight magnetic field in a straight linear direction or a cylinder. Let us say we take a cylinder and you have a magnetic field and the charged particle gyrate. You cannot keep that confined for long. However, there are ways to confine charged particle in a straight cylinder by tapering the magnetic field geometry. One such configuration is called magnetic mirror, where what happens is that you can imagine a magnetic field line a magnetic field, these green lines here in the screen represents the magnetic field lines, which are weaker at the center. Look at the inner line distance, they are larger, that means the magnetic field density is smaller there, line density is smaller, field is weaker. And the field lines are closer at the edge, so there is a strong magnetic field. Now what happens is that when a charged particle gyrates around such a magnetic field, it would have a higher gyro radius in the center, weaker field. As the field increases, the gyro radius increases. And eventually the particle would bounce back from the weaker field. It moves from the weaker field to the stronger field and it bounces back. It's like in a mirror, the particle would bounce back and forth. And this is why they are called magnetic mirror. You can have such configurations in a cylinder with various magnetic geometry, magnetic field coils. Now this was one of the ways people originally thought of the confinement. This would confine the charged particle. But one of the problem here is that we know that the work done by the magnetic field is zero, and if you have a completely parallel velocity, so if the particle has a velocity which is solely parallel to the magnetic field, then V cross V forces won't act, Lorentz force won't act. So the particle won't be gyrating around the field line. It will just transit through the mirror, through the device as if there is no field. So if you look at the right hand side picture, there is what we show here is the velocity Vx, Vy, Vz. So this is the velocity space. And V parallel is the direction, which is the direction of the magnetic field and the parallel component of velocity. Perpendicular components are Vx and Vy. So if the particle enters with a solely parallel velocity, let's say along the z direction, parallel to the magnetic field, then this would not see the magnetic trap, it would just exit. For any magnetic field geometry, one would define something called the ratio of the minimum to maximum minimum magnetic field. That is the maximum at the edge and the minimum at the center. If that is the case, then one can define a Bmax by meaning, which is what you call a mirror ratio, or the ratio of the maximum minimum field. And for any configuration of magnetic geometry or magnetic field values, one can find a small cone of angle, or where the inclination, so the velocity of the particle could be parallel to the magnetic field, or if there is a small angle between the magnetic field and the velocity of the particle, then these particles are not confined. You could imagine that if it is exactly parallel, there is no confinement. If there is a slight angle, yes, it could confine, but the confinement is weak, so the particle would not be effectively trapped in the magnetic field line. This is what you call the particles in this velocity space are lost. So what you call is a lost cone. And any other velocity, particle having velocity which is other than this tiny cone of cone, would always be trapped in this magnetic field. So what happens is that in a mirror, you will always have some particles which have velocity which is just right that they are not trapped. Those particles are called lost cone, and these particles are lost from the confinement. Now, this is a good idea that you can have a particle confinement in this way. However, what happens is that since what I said so far is a single particle, but in a plasma, there are particles, many particles, and they keep colliding between each other. During the collision, it may happen that some of the particles would gain a parallel velocity or a parallel momentum, and which makes the particle fall very close to or fall into the lost cone. That means their velocities are so high that they cannot be trapped in the magnetic field. So eventually in a plasma, the collisions among the particles keep pumping the particles into the lost cone, and you keep losing the particle. Therefore, a mirror machine in a linear configuration cannot be used for confinement for a long time. People have tried this, and what happened was the maximum gain, power gain that you could attain, even a theoretical limit, was roughly, for 100 kV plasma, it come out to be roughly 1. That means if you put 100, whatever power you put, you would only get that much energy as output. This is not a very good idea for a reactor. For a reactor, you would like to have a gain of 30, 50 kind of thing. That means you want to have 30 to 50 times gain in energy than the energy that you put in. It is not possible in a mirror machine due to this particular aspect of loss cone, where the particle gain the parallel velocity and loss from the device. So how can you actually improve this? One of the ways is instead of using a straight cylinder with tapered magnetic field, you use a closed circle or a torus. Now what happens is that the particles which could have lost here from the edge of the mirror would be now staying in the field. If you look at this way, so what you see here is the red tire kind of thing. This is the cylindrical toroidal vessel, and you have a magnetic field which is along the center, which is directed this way. And if you put a charged particle here, the charged particle would gyrate around the field line in a helical orbit, and the particle would not be lost because it keeps doing that forever if you have a single particle and the correct energy. Now, if you cut open a torus and see what has happened, that's what you see on the right hand side. So, if you just imagine that you cut open this torus, we need to define this to understand the coordinate system and how which would be useful in understanding the confinement in a toroidal geometry. So, what you see here is the vertical yellow line shows the center of the machine, which will be somewhere here, and you can see that there is what the capital R is the direction what you call a major radius, and inside of it you see that yellow circle which with a small radius R. This is the inside of the torus. Plasma will be filled inside, and this will be continuously toroidally continuous. So the phi represents the toroidal angle which is continuous inside. Now just look at this picture. What you see here that in the outer side the distance between the points are larger compared to the inner side of the circle. That means it's kind of stretched. It's like you can imagine like a rubber band which is stretched outside more compared to inside. This you can clearly see here. The distance between the 2 points in the inner side is much smaller compared to the outer side. So this represents the inner structure of the torus. Now we need to keep coming back to this picture again because this is important to understand how the confinement would work. Now if you just look here, because the magnetic, so here we have seen that just we bend the circle, there is a larger distance between the field lines on the outer side and the field lines are coming closer inside. Because of the bending of the field lines, now we have a curved magnetic field, and the particle which move along the curved magnetic field would feel a centrifugal force. In addition to that, as we saw, there is a gradient in the magnetic field, and there is a higher field inside and the outer field, lower field outside. So this gradient and the curvature, essentially what it does is that a gyrating particle would no longer gyrate in a given magnetic field line. Instead, it would start to drift its center. So the particle would eventually move from its original position to either up or downward. If you look in the picture in the left hand side, this is the cut open section of a torus. The torus continues towards the back, so it's what you call it is a poloidal view, where you take a poloidal plane. And because of the gradient and the curvature of the magnetic field, the ions would drift. The ions which have a higher Larmor radius, higher gyro radius, now drift towards upward side, and the electrons which drift towards the downward side. Because of this charge separation between the ions and electrons, this creates an electric field in the plasma. Now, you have a magnetic field which is already along the toroidal direction. So, this electric field and the magnetic field would cause a force on the plasma which would try to pull the whole plasma outward. So, this is not easy to confine a plasma just with a toroidal magnetic field. So, what can you do? The only way to, or one of the interesting ways to do this is to short circuit this electric field. Just by short circuiting this electric field, the E cross B forces, which is perpendicular to the electric field and the magnetic field, can be stopped. So, how to do this E how to cancel this for electric field is by using another magnetic field. So what happens is that if you have a magnetic field which is flowing like this in the helical direction, then this kind of take electrons and ions. Electrons would move upward, ions will go the other way, and then this would neutralize the magnetic field, the charge separation. Therefore, the only way to keep a toroidal plasma stable or in place would be to have a helical field. That means not just a toroidal field, but a field which is slightly twisted. So, how can you create such a field? In order to create a straight field, one of the you could use magnets, permanent magnets. That's one way. Another way would be to use current carrying coils, because it's easy to use a solenoid, and we know that a solenoid has a magnetic field which is largely parallel in the center. So, if you want to produce a helical field, one can use either a very complicated shaped solenoid which produces a helical field inside, or you can use a slightly simpler configuration by driving a current through the plasma. The former one, where you use the complicated coils, are called accelerators, and this is one of the ways to produce fusion, and this has been, the picture is taken from a picture of Wendelstein 7S, which is one of the largest accelerator currently being operational. And other way is to use something called a tokamak. Tokamak is basically toroidal chamber for magnetic confinement, and this is a Russian word which uses current carrying circular coils to produce a toroidal magnetic field, and you drive a current through the plasma to produce a magnetic field as shown in the green line, the green BP. So the plasma current produces a toroidal field, and the external current carrying coils produce a field which is along the axis of the torus. So the net field would be helical, like shown in the blue color. So, in such a case, we saw that there is no net charge separation between the electrons and ions. Therefore, there is no net electric field, and the plasma won't be moving outward just like that in a particle picture. So, how do you define the equilibrium? In the case of Sun, we have seen that it is the hydrostatic equilibrium between the gravity and the pressure forces. Here we have the pressure forces because we have finite temperature plasma inside. Now, this is balanced by the magnetic field outside. So, how the magnetic field, the balance between the magnetic forces and the pressure forces is what is a more tongue-twisting name, magnetohydrodynamic. And the equilibrium of the plasma in a tokamak is described by what you call, instead of hydrodynamic, you have a magnetohydrodynamic equilibrium. So, there are two types of forces one can imagine. One, just because you have bent a cylinder into a torus, there is a strong asymmetry of the magnetic field which creates a toroidal force. And there are radial forces which is coming due to the pressure and the current in the plasma. So these two forces are balanced by the magnetic field from the generated by various configuration. Now, one of the basic assumptions of the magnetohydrodynamic equilibrium is we are dealing with plasmas where which are velocities of the waves or any perturbation in the plasma or any wave in the plasma is much smaller compared to the speed of light. So we are essentially in the non-relativistic regime, and the plasma electrons, the time scale we are looking at, or the magnetohydrodynamic time scales are much larger compared to the fast movement of the electron time scale. So, one could imagine the electron inertia is almost negligible, or the electrons respond infinitely fast. So, we are looking at a global picture where the electrons and ions combinedly act like a single fluid, where the individual motion of electrons and ions are not important. And it's more like a fluid, that means there is collisions between the particles which equilibrate to a common temperature and so on. And we are looking at a non-relativistic regime. So, in this description, this is the slowest, one of the slow time scales. So, if the plasma is stable in a relatively low, slow time scale, then only one can think of having a sustained reaction, sustained fusion process. So, if you look at the forces on the plasma, As I said, we have, because of the stretching of the field line and the bending of the field line, we will have a force, net force, which is acting outward. One of the reason for this is, you can imagine like a tire tube, cycle tire or any tire, where there is a net force which is acting towards outside because of the pressure inside the chamber, inside the tire. Similarly, here you can imagine torus is let's say a tube which has plasma in it, gas in it, so it exerts a net outward force. Another kind of force which acts is that because of the current in the plasma, there is something similar to hoop force is acting, which is basically trying to repel the plasma outward. Then of course there is magnetic force which goes as 1 over r. So there are several toroidal factors coming into picture, and all that would like to push the plasma as a fluid, not as an individual charged particle as we saw earlier, but the whole fluid of the plasma eventually would be pushed outward. This is happening on a time scale much slower than the time scale of individual particle motion. So this is one type of force which is acting. Then, like in the case of sun, we said that there is a pressure inside and there is a radial force which is happening, and this radial force also will have to be counteracted by the magnetic field. So how do we counteract these magnetic forces? So one of the ways to counteract this would be to produce another magnetic field which is perpendicular to the torus. So it's called vertical field. So what you see here is again the cut open section of the torus, and you have current carrying coils outside which produces a magnetic field which is from up to down, top to bottom, like we see here. Now we have a current and a magnetic field. Current is flowing in the torus along the center of the torus, along the axis of the torus, and the magnetic field together form a V cross V force or a Lorentz force, which you also call J cross V force, because V is nothing but J eventually. So the Lorentz force is balancing the pressure forces. This is one way to pressure as well as hoop force and all the outward radial forces will be compensated by the J cross V forces. Similarly, the similar force balance also work for radial pressure balance. So the overall equilibrium of the plasma, we say in the case of sun we had the gravitational force balancing the pressure forces. Here we have the Lorentz force, J cross V force balancing the pressure forces, pressure gradient forces. Another interesting way of compensating this toroidal force balance would be to have an infinitely conducting wall. What happened is that if you have an infinitely conducting wall, let's say a superconducting wall, which is surrounding the plasma, then what happens is that when the plasma moves outward, because of all these forces, the plasma tries to move outward. When the plasma moves outward, it produces eddy currents in the wall, which create a magnetic field, and this magnetic field prevents the plasma motion towards the wall. So eventually you can reach a point where the outward force and the inward forces are. So the force created due to the eddy currents, the magnetic pressure created due to the magnetic field of the eddy current, and the plasma would be balanced. But this is not possible. Although theoretically this is possibility, in a fusion reactor this is not possible because you have fusion product like neutrons and high energy particles in the plasma which would interact with the wall, and this create defect or produces defect in the wall which reduces the conductivity, so or increases the resistivity. So you can't have a infinitely conducting wall in the first wall, but theoretically this is a possibility of reducing the or keeping the balance equilibrium, at least as a toy problem. So if you look at the tokamak schematic, how would it all look like? We have set up so many magnetic field. How would it all in reality look like? So what you see here in the purple color is the vacuum vessel, which is a stainless steel vessel, a finite conducting vessel, vessel with a finite resistivity, and the tan colored things what you see outside is the toroidal field coil or the toroidal solenoid, which produces current passing through them. It produces a magnetic field along the axis of the torus. You see the dark arrow here. Now there is another solenoid here which produces, using which you start the plasma. Basically what you do is you create, you ram the current in the solenoid, which create a dP/dt, a change in magnetic field, which induces a current in the plasma. So there's a solenoid act as a primary of the transformer, and plasma is like the secondary of the transformer. So due to the transformer action, you can produce an electric field here, which drives a current again parallel to the axis of the torus, either parallel. So it is in the same direction as the magnetic field, toroidal magnetic field. So this together produces what you see like a helical field here. The the black lines which are the helical field. You see that they go around the axis of the torus. Now the red colored coils which you see outside are called poloidal field coils or the vertical field coils, which are basically aimed to produce a vertical field to balance the hoop force or the pressure forces which is pushing the plasma radially outward. So these red colored coils are called poloidal field coils or vertical field coils. So keeping this kind of magnetic field geometry would create a equilibrium. Now the question is, how stable is this equilibrium? Stability means if you just perturb the equilibrium, then would it actually go back to the original state, or would it destroy the stability of the plasma? And how good is your control? Now, one aspect is that in the magnetohydrodynamic picture, plasma is a fluid, so is the magnetic field. So the plasma and the magnetic field would like to stay together. They are like wind together, and one of the conditions is that if the plasma resistivity is very small, or if the plasma is a highly conducting medium, the resistance is very small, then plasma and the magnetic field line would move together more like what you call a frozen in field line. So one could imagine that there is a plasma as a fluid and magnetic field is another fluid. Now what happens that if you perturb such a field line, there may be a situation where you look at the third picture here. Plasma could be a heavy fluid and magnetic field would be a lighter fluid. This would be an equilibrium, surely. But when you perturb this equilibrium, eventually the blue colored heavy fluid would like to come down, that is our plasma, and the low field would go inside. Similarly, in the case of plasma, if you perturb the outer field side where there is a weaker magnetic field and the plasma is strong, if you perturb the plasma would come out more like a balloon or something, or a bulge outside, and these are kind of the instabilities present in the plasma. So the instabilities in the plasma could be either due to the pressure gradient or due to the current cases. Current determines stability. This limits how much temperature and how much current can you drive in the plasma, how much pressure and temperature can you achieve in the core of the tokamak. So the stability criteria of the plasma decides so there are various stability limits on pressure and the current. And this kind of controls how much pressure can you achieve in the machine for a stable operation, and or how much current can you drive in the tokamak to achieve a given magnetic field. This is something is one of the core aspects of a reactor optimization, where to find out the stability and the stability regime of a machine. One of the thing is that we would like to have a plasma design where it is at least not responding to the macroscopic instability, because what happens is that if you have a magnetohydrodynamic instability, the plasma as such is moved out of its original position, and this could fall on the wall and could be detrimental and could also induce huge current in the wall, which could create eddy currents and eventually destruction of the machine. So one would not like to have large-scale emerging instabilities in the plasma. Therefore, when one has to find out the optimum window of operation of pressure, temperature, and current, this is one aspect of the reactor design. Now, the main purpose of the magnetic field is to confine the plasma as well as to keep it away from the wall. In the case of a stellar equilibrium, we did not have this problem of keeping it away from the wall because the gravity did its job. But in the case of magnetic field, we are making the plasma in a vessel, and the vessel temperature are like maybe 600 Kelvin, 1000 Kelvin at max, and the plasma having a very high temperature in the core. So you wouldn't like to have the plasma moving out from the core and depositing all its energy in the wall. So the plasma, how good the plasma confinement is, how the energy is transported from the core to edge, because if the energy is lost from the core to edge, the plasma confinement is plasma temperature goes down. You don't want that. So this is one of the major active area in the fusion research, that how the plasma energy is transported and how can you minimize its impact on the walls so that the walls can survive longer. In the right hand side picture, what you see here is a plasma produced inside a tokamak. So what you see here in the dark central point is the central portion, the inside of the plasma, through which the solenoid and are inside that, and the dark region is the plasma, where you don't see any light emitting because you have no radiation from there. It's a hydrogen plasma, so if it is ionized, there is no excitation, line excitation, so that's completely dark. And the pink region, what you see is the region close to the wall, where there are a lot of hydrogen neutrons present, and because of the excitation and ionization of them, the excitation gives light. So the pink color, what you see here, is the light from the plasma. If you take a colloidal cross section of such a plasma, one of the things that you notice is it's no longer circular, it has a shape. It has a balloon-like shape with the two tail-like things at the edge. This particular thing, that shaping of the plasma, is another important aspect of fusion research, especially for sustaining long-term operation of the plasma and to have a high temperature and high current in the system. Because shaping of the plasma would actually help you from going from circular to an elongated plasma would help you to drive better current in the plasma, to go to a higher stability regime, and therefore possible to achieve higher fusion, higher plasma temperature. Now, what we also saw that from the picture on the right hand side, you have the walls here, the grey shaded region is the wall in the picture. The plasma is kind of detached from there, and only in a very tiny region at the bottom, the plasma is actively in contact with the wall. So what happens is that the energy which is in the core of the plasma, several megajoules of energy, is transported from the core to the edge. Edge is like the close to the wall, from the center to the outside, both parallel and perpendicular to the magnetic field. But along the magnetic field line, the charged particle will travel, most of the energy is transported, and the plasma and the interaction of the wall is limited to a very tiny region, what you call far away from the main plasma. What you call this region is a diverted region or a diverter, and these plates are called diverter. So the plasma wall interaction essentially is confined to this particular small tiny region, or ideally you don't want the plasma to interact with any other parts of the vessel. Although this is ideal, in reality there will be always perpendicular transport of charged particle across the magnetic field line, and this would result in strong plasma wall interaction everywhere. But most of the plasma wall interaction is confined in this region. Now, we don't want also a lot of energy, like several megajoules of energy, or is coming from the plasma, would be deposited on the wall. Instead, we would like to radiate away this energy. So the plasma energy which is conducted from the core, you don't want that to be depositing all that energy onto the material wall, because this could raise the wall temperature to several thousands of Kelvin, which can melt or sublime the material. Therefore, it is important to radiate away the energy coming from the core to the edge. And this also puts a critical condition on the material aspect of the material part, the plasma wall interaction aspect, because once the plasma, so basically the problem is you have to design ways in which there is an efficient radiation of the plasma at the edge region. In the core region, you don't want to radiate the energy, you don't want to cool the plasma, you want the fission reaction to take place. But the edge region, you want to efficiently radiate the energy by excitations and so on, such that the energy dumped on the wall is minimal. This is one of the major topic of research right now, to how to have better optimized ways of doing it, and how the magnetic field geometry and what kind of instabilities we put together. Because see, the core plasma is not completely detached from the edge. So whatever happening in the edge would also have an impact on the confinement and the stability of the plasma. So one of the active area is to how the wall properties would impact the edge properties, the core properties and the confinement and stability of the plasma. And this diverter configuration with advanced diverter configuration is another area which is currently very interesting. And another point is, when the plasma interact with the wall, like you see here, it would sputter the particles from the wall, it will remove the particle from the wall by momentum transfer, by the collisions, and these particles would go into the core of the plasma by the transport process, by collisional transport. This would also radiate the plasma energy from the core. So therefore, it is important to keep the plasma core as pure as possible. Pure means you have only Dt and a bit of helium, which is also forming in the core, so you need to remove the helium from the core as well, but not to have too many impurities going into the core of the plasma. So this controlling of the plasma transport, back impurity transport, and how that would design, or how that would affect your stability and equilibrium part, is developing advanced operational scenarios for the tokamak. And after all, the material property, like whether it has very high number of electrons like iron, or if you have the wall which is made of steel, for example, or tungsten, it has many electrons, and if that goes into the core, it would radiate away all the impurity. But so the tailoring the material property, having better materials for wall, and diverting the heat in a way such that better diverter configurations have to be designed. These are some of the interesting area of current research. Now, if we just look at the history of the tokamak, the idea of tokamak has started somewhere 1950s, and T1 was the first tokamak in Russia. So you see that here, the basic stability condition was proved in such machines. However, due to the presence of the walls which are very close to the plasma energy was mostly radiated in the core, or 80 to 90% of the heating which was given to the plasma was radiated instead of doing fusion. The tokamak research continued to evolve in the next 2 decades, and there are several landmark achievements have been obtained, including that one could find the temperature of the plasma could reach up to 1 kV or so. This was one of the important landmark point in the tokamak confinement. Another important point was the tokamak transport. Compared to the linear machine, the confinement and the transport was much slower. Confinement was better and the transport was slower in the case of tokamak. This was one of the important achievements making tokamak research, pursue tokamak research for fusion. And the tokamaks around the world continue to evolve as time progressed. So you see on the left hand, there are 4 tokamaks here. One is the left hand side tokamak, which is in French tokamak from TA 2000. And then this is one of the largest tokamak we have, that is JET, which is shown that joint European torus, which has shown that fusion reaction is possible. We have a tokamak, superconducting steady state tokamak from India, which is in its revamp phase right now. And we have another tokamak which you see on the right hand side is it's a full metal machine, steady state long pulse machine in West, in France. And there is another tokamak in India which is called ITER tokamak. It was one of the old first tokamak which has now been upgraded and able to handle shaped plasmas and so on. So around the world, tokamak research continue to evolve. And so is the fusion power. So fusion has been demonstrated successfully. If you look at the right hand side, this is the left hand side is a newspaper press release from the joint European torus, which was able to show 17 megawatt fusion power in 1997. And what you see in the right hand side is the fusion achieved in different machines and the fusion power that one could get from those machines. There is one number that you see here is called Q. Q defines the power gain from the input power. So Q equal to 1 means you put whatever energy and you gain that much energy from the fusion power. So you see that in most of those cases, the maximum Q achieved was 0.6. That means you gained much less fusion power than the power that you input into the machine. So an economically efficient viable condition has not been obtained so far because of the size of the machine, because of various constraints from the heating and so on. Now, to achieve a machine which has a Q which is much larger than 1, so that it is possible to have a fusion reactor, is the current aim, and that is where the current research is going on, like ITER, International Thermonuclear Experimental Reactor. Now, in here, one of the goals of ITER is to show that you have a net power gain of 10. So you have a 500 megawatt fusion power is planned to show, it is aimed to show, from an energy of roughly 50 megawatt input. So you get a net power gain of 10. Now, how robust or how good is this prediction, or how do we trust that this is possible? That's what we see here. In this picture, what we see here is what we call a confinement time. Confinement time is like how much time can you store the energy in the plasma. It's energy confinement time. So it's like you switch off the power and then how much time can you actually keep that energy in the tokamak before losing. So if you look at here, if you switch off the heating power, of course. So what you see here is, in the x-axis, you have the scaling of the fusion power, confinement scaling, from scaling of the confinement time from various machines that has existed. And on the y-axis, what you have is an experimental confinement time. And you see that all the data points, blue, pink, whatever data points you see here, they are all lying in a straight line, passing through the center. So this essentially shows that the confinement time prediction that we get from the machines currently, and you look at ITER is on the top, which is exactly lying on the same line, indicate that the scaling of the confinement time for ITER is very robust. Now, why this is important? Because in order to achieve economically viable or a condition where you can get a net power gain is something what is called performance of the tokamak, which has been characterized by a figure of merit, which is called n t tau e. So n is the density of the plasma, t is the temperature of the core, and tau e is the confinement time. So the criteria is like a figure of merit, which has shown that this n t tau triple product should be larger than 5 to the power 21 for having a reactor-like condition or a self-sustained ignition condition. Let's say that you have a Q which is much larger than 1. Now, if you look at ITER, so here what you see in this picture is the central temperature of various machines in the world in the x-axis, and in the y-axis you plot n t tau e, this triple product, density, temperature, and the confinement time. And you see that the DFDR, which was shown to have 10 megawatt fusion power, another mission aspects upgrade, jet, they are all lying in one curve, and the reactor conditions are shown here in the uppermost curve. And ITER is lying very close to the reactor condition. So the confinement scaling has to be extreme because we can decide N and T from the stability criteria, but the confinement time has to be calculated from the power balance and various kind of other scenario which comes into the picture, like how the heat is transported, what kind of stability criteria you have, and so on. So this confinement time scaling essentially shows that ITER is exactly in the same path as the other machines, or we can predict the confinement time much precisely, and therefore the ITER machine would be very close to the reactor conditions. Now, just have a quick look on what ITER is. So this is a schematic. This is a picture of ITER, and this is taken from the slide. And what you see here, it's a giant machine, and it has altogether a weight of 23,000 ton with a central temperature of 150 million degrees centigrade, that's like 15 kV, and it is expected to produce roughly a fusion power of 500 megawatt. Now, the height of this machine is roughly 30 meter. What you see here is the total height is roughly 30 meter, and that's like a 10-story building. And the machine major radius of this is like 6.2 meter with a minor radius of roughly 2 meter. So with a total plasma volume of close to 1000 meter cube. So that's the kind of machine is being built, because size does matter if you want to have higher fusion power. And some technical aspects of ITER. So ITER is a machine which is built by several, it's an international collaboration with different countries around the world, and different people, different contributions from different countries are in kind, means we manufacture and then ship them and assemble them at the ITER site. So we can see here in overall various countries contributing to the ITER project, where India is also a significant contributor with 10% of the total ITER contribution. And various, I just want to show you the different components of the machine, which is being manufactured in different parts. And just for comparison, you can see here, this is a TF coil, the toroidal field coil, one of the coil, 18 coils, of which one of the coil, and you can see the people standing inside. So the size of the machine can be compared. The ITER, I just want to show you that there is something interesting happening in ITER. So if you look from 2016 to 17 to 2020 on the top and bottom, but you see that there is a constant progress in the ITER construction, and the ITER site is coming up. So this is expected to have first plasma soon. And coming to India's contribution to ITER, India is basically the Indian part, the domestic agents responsible for India's contribution. And what you see here is a ITER campus with the ITER India building, the tall building, which you can see here with practically no windows. That's the labs of ITER where the testing of components and so on going on. But yeah. So if you look at this picture, this is a cut open cross section of ITER with various things. And India's contribution to ITER is basically 9 packages, where the outer there is a cryostat, which is like a vacuum jacket. So inside, it's like the thermostat, inside which the whole building, whole ITER is housed. So it's like it is keeping the interior of the machine cool from the outside temperature. And this has a height of roughly 30 meter and a radius of 30 meter. And so it's like a 10-12 story building, which is completely manufactured in India and then assembled there. Then we have shielding for various components from the neutron bombardment because of the fission neutrons. Neutrons practically pass through the plasma. Plasma is kind of transparent to them and they interact with the material, and eventually it will hit the superconducting coils, which carries huge amount of current for this magnetic field, and the neutrons interact with the, in order to prevent the neutron interaction from the magnetic field, you need to provide shielding, which is done in India. Then there are various kind of heating for the plasma. So as I said, plasma is a conductor which does not resistively heat beyond a certain temperature. So one has to go for additional forms of heating like radio frequency heating, neutral beam heating. Then there is, in order to, once we have the fusion reaction, there is heat is generated and the heat needs to be extracted out using cooling water. And the water for this heat exchanger is provided, and the cooling water system, which is not just the water but the heating system, cooling system is provided. Then there is, we need to keep the coils at superconducting temperature to carry large amount of current. So the coils in tokamaks, in the modern day tokamaks or advanced tokamaks, what happens is that the current, the magnetic field that you require to produce the kind of confinement is of the order of several Tesla, like 5 Tesla for example, in ITER 5.3 Tesla. So in order to produce such high magnetic field, one needs to have very high current passing through the toroidal coils, and these coils has to be superconducting therefore. And in order to keep them superconducting, one needs to have to go to low temperature like liquid helium. So in order to go to such low temperature, one needs to have successive cryo distribution, or the supply of liquid helium and liquid nitrogen, and that is done by cryo distribution lines and cryo lines, which is also part of India supplying, and there are power supplies for various heating and current drive systems. So that's basically overall India's contribution, and India also has a blanket program which is basically to try and develop technologies for generating, extracting heat as well as precision building, both. So that is the India's contribution, and what we are not contributing is the magnets, which are, we saw that there was a picture where people are sitting inside the magnet field coils and so on, so they are developed by other people, other contributors. Then solenoid magnet, then shields of various other type of shielding, then diverter, the heat handling part which we are not doing, colloidal magnetic field fuel cycle, this is supplied by other people. That's how the ITER is built there. And if you I just want to show you a quick view of ITER cryostat, which is basically is in 4 sections. So what you see, this whole thing is 30 meter height, and you can see a sketch of a person here. So one can imagine how the ratio is. And this has 4 parts. There is a base plate, then there is a lower cylinder, upper cylinder, and then finally the upper plate. So it's basically, cryostat is a vacuum vessel that inside which the whole tokamak is situated, and it provides kind of a thermal shield. It's like a flask which kind of provides a thermal shield from the external world to the internal cooled components. And the cryostat is base installation has finished in May 2020. So it has been made in India. Like you can see that this is built in India with various people, and then it is finally assembled in the ITER site. And the cryostat base installation is started is finished, in which the whole machine assembly will be carried out. Similarly, the cryo lines are installed, and what you see here are the cryo lines and cryo distribution system from again another India's package, and involved shields, which is the neutron shield for the blanket for the TF coils. And lately you see that September 20 India has completed its involved shielding package also. Similarly, cooling water system, which is basically to so the heat from the tokamak comes to a primary heating system, and from where the heat has to be extracted. So ideally what happens is that in a reactor what happens is that the heat would be converted to electricity, but in ITER it is not. It will be extracted, the heat will be going back to atmosphere, and that is done by cooling, primary and secondary cooling water. The cooling water system is happening. And if you look at India's activity on site, this is the whole ITER site, and you will see that there are various parts, and this is the cryostat workshop inside which the whole cryostat was assembled. And then it moved from here to the tokamak building, and and the assembly was happening. What you see here is a huge, this thing is a tokamak building which has a 60 meter pit inside which the cryostat base plate is lowered, on which the assembly of the other things would happen. Similarly, one can see other uh, current drive and heating and cryolines and so on. So essentially, what happens is tokamak is a large magnetic cage, and you produce intense magnetic field by powerful superconducting tokamaks. And this magnetic field is capable of holding the plasma at a high temperature for a considerable period of time, which makes fusion reaction possible. And the magnetic field also prevents, to some extent, keeping the plasma interacting with the wall, or keep the plasma inside, so that the confinement can be improved. And if you look at the magnetic field geometry, it has a one central solenoid and then 18 toroidal field coils to produce the magnetic field of roughly 5.3 Tesla. And they are of 70 meter high, and each of them has a 360 turn weight. And there are 6 colloidal field coils. You see this red colored thing is the colloidal field coil in ITER, which is providing the correction field for various force balances. It's very strong magnetic field. Now, if you look at the recent advances beyond ITER, or the current trends, is the machine size can be considerably reduced provided you have very high magnetic field. So currently, the magnetic field is limited by the superconducting coils and also the technology required to keep the coils cool and so on. But if there is another trend, that is, there is high temperature superconducting coils which are being developed. So the advance in the high temperature superconductivity has made extremely powerful magnet of the order of 10, 12 Tesla are possible now. People are experimenting with that or designing with such machines, which can go back to extremely compact machines. Like right now, the machine size is 6.2 meter. But one can go to half of its size, let's say, by extremely good high power magnets. So that is one area where the current research is going on. Another aspect is when one goes for a higher power machine, small size, the heat which is transported away from the core to the edge, it requires handling. So one needs to have novel designs for heat handling at the edge, which would impact the confinement. Another important point is how this would impact the confinement. So there may be confinement regimes where one can go for higher density plasma and with higher magnetic field, one can go for higher density, and also with shaping of the plasma or going to different designs of tokamak. Instead of going to a large aspect ratio machine, large size machine, one can go for a more compact machines, which would improve the confinement regime. So for higher plasma pressure is possible, and so on. These are the recent and current trends which going on in the area. Now, having said all that about tokamak, plasma is one of the most abundant state of the visible matter in the universe. So it's not only in tokamak. If you look at the whole spectrum of plasma, you can see that the plasma in the space plasmas or the plasmas which we see in nature have a very low density, high temperature, whereas the tokamak plasma lies with a moderately high density and very high temperature. You can have an alternate concept of fusion, which is not magnetically confined, but by inertial confinement. Inertial confinement means you can make very small pellets of deuterium and tritium, and they can be inertially confined by using lasers, and can produce very high power fusion. This is another area of fusion energy which is currently being pursued in various parts. And this inertial confinement fusion is something which can produce high fusion power for a short while, because the confinement in such system is by laser. So the confinement time so far is proven to be very small, but there is active research going on in this area to have a high confinement inertial fusion, and the densities are getting closer to solar core. You see that it's only few orders of magnitude, whereas in the case of tokamak, magnetically confined tokamak, it was roughly 15 orders smaller than the solar core. Now, there are other, of course, we know that there are fluorescent light, flames, lamps, is also constitute plasma. There is another interesting class of plasma which exists, is basically relativistic plasmas, like where the temperature is roughly more than 10 to the power 9 Kelvin, where the plasma electrons follow the relativistic when the energy is more than the response energy of electron. Such plasmas are observed in nature in accretion. It is in the accretion of matter, and for example the active galactic nuclei and so on, or plasma accelerators. This is another area where, or plasma based accelerations, there also the particles are of relativistic nature. One can also find quantum plasmas. They are actually truly exciting class of plasma which are basically having very strong coupling. So in all the plasmas that we discussed in tokamak, the kinetic energy is the important factor. The potential energy is small, that the coupling between the particles we could consider more or less their ideal areas. So the coupling between the particles was not so strong. But another interesting class of extreme case is strongly coupled plasmas, where people say dust interaction in plasma in space as well as in laboratory plasmas. Then solid state plasmas, and quantum plasma is currently an emerging area of interaction. Then there are exotic plasmas like quark-gluon plasmas and so on, which are again another interesting area. So essentially plasma forms an abundant state of visible matter in the universe. And studying about DOM is indeed exciting. In addition to fusion, there are various other exciting natural phenomena one can study. Also, there are a lot of plasma applications, which is another area of plasma research. So basically, atoms, plasma is a soup of atoms, molecules, ions, electrons, radiation, and everything. Together, they form an interesting field of study. And what you see here is a picture of Aurora Borealis, which is the northern lights which you see in the northern hemisphere, which is again a plasma activity. So thank you very much.
Thank you. Thank you, Dr. Maya. It was a really nice talk. You spoke really well and we have enjoyed it. I'm sure everyone has enjoyed your talk. I would also like to tell you that in this seminar we had only 2 women speakers and you are one of them. And yes, yes, and the talk was really nice. Okay, so now let us take up some questions from the audience. So is there any question? You can switch on your mic and introduce yourself and ask a question to directly to the speaker. Is there any question from the audience?
I want to ask some questions now.
Yes, sir. Sure.
This is Shaikot from Bose Institute. So you told first thank you for the nice talk. You told for high magnetic field you need high current. So for production of that current, the power supply you are building in India or somewhere else?
For the magnet?
Yes.
For the magnet power supplies, we are not building in India. What we are building is mostly the power supplies for the heating and current drive systems. So they are like pulse power supplies and so on for the heating and the current drive, not for the magnet.
And from where you will get the power supply for the magnet?
I think some of the contributors are making, I'm not sure who is building that.
Okay.
Some of the TF coil supply, I'm not sure.
And what will be the value of the current? Like you told magnetic.
It will be like 160 megaamps kind of thing roughly.
Okay.
Total current. So per coil will be divided by 18, and that is the current of individual TF segment. So that's 18 segments from the solenoid.
Okay.
So yeah, I'm not sure who supplies them. I'll check and get back to you.
Okay. Okay. Thanks a lot. Okay.
Thank you, sir. Anyone from the audience who wants to ask a question? I don't think so. I think Abhishek Treva has a question.
Yep. Yes.
Hello? I see his mic is switched on, but he's not speaking. Okay, maybe someone else. Someone else can ask a question in the meanwhile, or I can.
Can you hear me now?
Yes, yes.
Okay, wonderful. So my question is about the energy transfer that you were saying that the plasma actually there is an energy transfer from the core to the walls, right? So what you initially tried to do was you put in different kinds of magnetic field to stop the movement of ions and electrons, and hence so you do not have a net motion of the particles from the center to the walls. And also you actually nullified the pointing vector E cross B. You also nullified by putting an extra magnetic field.
Correct.
That was giving it an extra force to move outside. Now, what is leading to this transfer of energy from inside to outside?
So there are 2 points. First is that when you start the tokamak, when you start the discharge, you have initially you start by switching off the toroidal field coils, then you fill the gas and then you start the discharge. Then eventually what happens is that you create, when you start discharge, you also build up something called a loop voltage, which is consequence of the solenoid discharge. Okay, then what happens is that you have some kind of a error fields are created, which will push the plasma out. In order to prevent that, you are using the vertical field coils, which could be either superconducting or resistive coils, normal coils, depending on how fast you want to switch. So you apply the power, you apply the magnetic field from the resistive coil to create an equilibrium in the first place. So this is something, a dynamic process which is happening. So sometimes it may happen that your vertical field current is not correct, or something else happens, or in such cases you may not even strike the discharge. So in order to get a plasma, you need to have the vertical field coils switched on at some point, and depending on how fast you want to reach the equilibrium, you will have to use various kind of current and coil combination. This was the point I said first. Now the E cross B force is happening. Had you had hello? Can you hear me?
Yes, we can hear you.
Yes.
Had you had only a toroidal field alone, there was no poloidal field, let's say, then what would have happened that there could have been an E cross B force, which is there could have been an electric field arising purely due to the gradient and the curvature, which is purely due to the toroidal geometric effect. Okay. Now we cannot have that condition in a tokamak because we should have a helical field to cancel us out quickly. So this is pretty much established in the very beginning itself. So the overall motion of the plasma outside was more like a time scale which is slightly larger than the E cross B force cancellation time scale. There are 2 different times. One is a particle picture problem and other is the plasma as a fluid altogether moving outside. So that was the initial startup phase. So this is something only if you can nullify the force can you create the plasma. Can you have a stable equilibrium. Now once you have the stable equilibrium, let us say there will be plasma is a dynamic entity. It is not a static equilibrium. So there will be always some perturbations, especially when you drive the current. You have, or there is pressure gradient. So you will always have some kind of perturbations and instabilities happening. This would also cause the plasma to move out from its position. This is what happens in the case of, let us say, the MHD instability. So one thing what we want to avoid is the overall motion of the plasma. So there could be instabilities which is happening inside the plasma, which does not move the plasma but cause mixing of the energy and particle, like sawtooth oscillations, for example. So there will be oscillations and instabilities happening inside, which helps the plasma to mix the energy and so on. Sometimes it's good, sometimes it's not good, depending on the situation. But this may not necessarily result in the overall motion of the plasma. However, the MHD effects, such as the ballooning modes or kink instabilities, which what actually does is that it moves the plasma from its position towards outside. This can have detrimental consequences. For example, you can create, let us say, eddy currents, or sometimes the force is so high that you could eventually tear apart some of the physical components. The electromagnetic force is so huge. So, yeah, this was the point I was trying to tell next. And there is always a convective motion of the plasma. Plasma would always transport across the field line by cross field transport. And so you have parallel, it's a dynamic system, so parallel and perpendicular. So, for example, collisional transport or turbulent transport and kind of various or anomalous transport, let's say. Plasma transport is not always collisional, you have anomalous transport also. This would move the plasma from inside to outside. And these are not something where the whole plasma is moving, but plasma energy and particles. So you reduce the confinement time, you lose the energy, you lose the particles, but not the overall physical boundary of the plasma is moving. And this can create, this can deposit energy to the wall. That is where we have the local problems of diverter heat handling, where if you deposit large amount of energy in a small event, like ELMs for example, these are like bursts of energy which is coming out from the core to the edge. It's more like you have very high frequency ELMs which dumps small amount of energy, or giant ELMs which can dump up to gigajoules of energy from the core. So it's possible that you have very huge instabilities happening, very huge occasional throw-out of energy or instability or turbulence happening, and this can also dump energy to the wall. This is something one can only do when one plasma operation happening, and one can do, like for example, there could be perturbation coils present which could tune in such a way that those ELMs can be suppressed. There are ELM suppression is one of the important problem or one of the important tasks people do in various machines. This was one thing. Other thing, there are developing scenarios or operational scenarios where you can have quiescent plasma. This is another aspect. So these are the things which happens while the system is plasma is, let's say, on, and the plasma is not physically moving from its boundaries. It still happens so that the plasma throws out its energy and the particles to the wall.
So mostly when these transfer is happening, it's mostly because of the anomalous behavior and the instabilities that are growing, and that is essentially out of our control right now.
You have some instability control. For example, there are ELM control coils which can actually control the which can create some resonant perturbations and which can control the ELM triggering frequency and so on. This is one way. Other way is to look at shaping the discharge conditions. Like there are modes which are called high confinement modes, where what happened is that the plasma in the core is very you have a high more like a flat density and temperature profile in the core plasma, but there is a steep gradient in the edge. This is one of the things which trigger ELMs because of the steep gradient of density and temperature towards the edge. So what happens is that one could actually tailor this, and there are new confinement modes people are coming up with, like machines are showing, where you could have a good temperature confinement but maybe slightly worse energy confinement, particle confinement, or slightly steeper profiles and so on. So there are modes people are trying out to have a better plasma, but right now this is a research area, yes, to develop advanced scenarios.
Okay, thank you. Thanks a lot.
Okay, there is one question in the chat box by Deeptok Bishash. He says, "Hi everybody, I have a general question which might have been already discussed in the first few slides. Can one plan to utilize this as an energy source?"
Yes, that is why we want to do it. Yes, indeed. We want to utilize fusion as an energy source. That was the motivation of the okay, so I was probably not very clear in the beginning. Why we want to study fusion was basically we want to produce energy from this. That is the overall objective of this work. Was there any, is that what you asked, or you want some more specific?
There is one more question from Deeptok. He says, apart from the general physics interest, is the generated huge energy applicable to industry or small scale energy generation?
Yes, it is. It is. That is why there are, so basically there are two aspects. One, the idea would be to have a large scale machine or a huge, so currently what ITER does is, ITER is trying to show that you can have a fusion power which is much larger than the power that you input into the plasma. This is one of the criteria that we must have to be able to run a reactor. Okay. The second aspect is there are advanced machines which is coming up right now, which is a small scale machine in a trial phase, where they want to show that in a small scale machine also you can produce fusion power to a sufficiently large amount, and then you can run a turbine. Eventually you can extract the heat and run a turbine to produce small scale electricity. This is also a point. And in the future reactor, like demonstration reactors, so ITER is not going to produce power from electricity from it. What it does is it extracts the energy and then it goes to the secondary heat rejection system or cooling water and finally throw the energy to the atmosphere. It is not really utilizing that energy to produce electricity. But demo reactor and the plan of fusion energy program is essentially to produce electricity from there. So you will extract the energy of the neutron. So the neutrons, which has 14 MeV energy, is eventually converted to, so you extract that energy in the form of heat, and this heat would be eventually utilized to run the turbines and produce electricity. So this is the aim of this whole exercise. Actually, that is the aim with which one does the fusion research. I think probably I was not very clear in the beginning. I'm sorry.
Hello. No, it was okay because I was little bit late for the meeting, so I missed first few slides.
Say again, please.
So it may be that I was late in the meeting, so it may be that I missed
No problem.
few slides.
No problem.
So thank you, Maya.
Thank you, Deeptak.
Okay, so is there any other question from the audience?
Yes, I have one more.
Yes,
Okay.
yes,
It's
sure,
not a
sure.
problem. So it's more about something that you didn't talk, but you mentioned in your few slides, last slide or second last slide, where you were talking about the laser accelerators, where your densities were going much higher. And I mean, this is more related to the field I have worked on, and most of the people here in Bose Institute work on.
Okay.
The densities that you were saying, they were going very high, close to the sun's core. So you think it could be possible to have the energies and densities that could take us to quantum regime?
Yeah, in the case of laser and plasma, they are primarily, you do have quantum, you might have actually quantum mechanical effects also. Yes, that is possible. And also there is lattice fusion and other kind of concepts are coming up. So yes, quantum mechanical or quantum plasma.
The reason being is that in particle physics community, getting a bigger accelerator going to higher energies is becoming more and more untenable, which is going to be a bigger problem for the community in general in future. So I mean, if you can get a linear accelerator, the kind of one which you showed using laser to get very high energies, right? It would be very good for at least particle physics community.
Right.
And
there is another scheme which is plasma-based accelerators. This is another area which I did not mention much in the talk, or didn't mention at all actually. Was plasma-based accelerators is another area which is people are working on, where plasma-based particle acceleration, which can go beyond the conventional acceleration regime. And there is it's a laser plasma interaction, and plasma-based acceleration is another important area. Yes, that is one also in perspective going on research in that area. Yes, it is a very active area too. So one can look for plasma-based laser plasma interaction and plasma-based acceleration. So there is
what India's role in these? So ITER is not a part of this, which I can understand. But any other group in India is working on these aspects?
Yeah, so laser plasma interaction, there was a group in IPR, TFR and so on, they are collaborating, and I think they have excellent work going on in that area. And inertial fusion also, I think there are some theoretical, I do think that TFR might have some, I'm not sure, but theoretical interest is anyway going on. So laser based inertial fusion has 2 points. First is, so there are 2 aspects. First of all, you have to make a pellet, and then you need to compress it, and using lasers, and you create a plasma. This was the first aspect. Second aspect is basically once you have the plasma, how the plasma is stable and how that laser plasma interaction happens. This is something actively going on in TFR and IPR. I think theory division was also working extensively in that. And about the plasma acceleration also, there is a lot of interest going on, laser based plasma. They both are going side by side kind of thing. So there are two aspects actually, but they are both essentially utilizing lasers. Yeah. There are several groups in India working.
Thank you.
Yeah.
Thanks a lot.
Okay, so if there are no other questions, then I think it is time we will close today's seminar. And thank you once again, Maya, for
Thank you
this
very much
such a
for
nice
having me,
talk.
and I'm really I thank all of you for joining this in spite of having the holidays and so on. And I'm really honored to be invited for this. So thanks a lot.
Yes, yes, yes. Thank
Okay,
you.
before we close the meeting, on behalf of the CAPSS Project Group, I want to thanks all our organizers and those who listened, all the speakers, including today's excellent contribution, all our faculty members for their encouragement, and especially a thank to our really efficient host Shreya, who managed all these lectures very efficiently. Thank you.
Not
All our
efficiently,
lectures
I
are
don't
there in
think
our
so. Thank you, but still thank
okay,
you.
all our lectures are there in our YouTube channel, Nature as we unfold it. Those who have missed some parts can go there and check it out. You will enjoy all of them thoroughly. That I can assure you. So I thank today's speaker once again, and thanks the audience. Thank
Thank
you.
you.
Thank you very much, and I have a very happy New Year.
Yeah, very happy New Year to
To all of you.
Let's hope it will be a better year. Thank you.
Yeah, very much. Yeah.
Bye.
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 यार जैसे ही बाय करने लगा